Okay, lecture 7. Today I'm going to cover dot products, which is just something that I kind of missed as we were kind of going through the material. And, just for completeness, we're going to make sure that you have this. It could show up from time to time. I gave a couple of homework problems on that on the last homework set, so I'm glad you'll get a chance to look at that. But I just want to make sure that you've seen it, and then I'm going to kind of do some review for the exam coming up. So the first thing I want to do is I want to define the dot product. If you have two vectors, so we'll just, this will be the dot product. Okay. Your book actually calls this the Scalar product, which is another name for it. There's, no right or wrong here. And sometimes because of, there goes my dog. And sometimes you'll hear this called the inner product, okay? And that's based on some indices from just some vector notation. You'll usually hear me call it the dot product. Your textbook's going to call it the scalar product. So either one of those. And basically what it does is it says if you have if you have two vectors and you dot them, okay, then that is the magnitude of A times the magnitude of B times the cosine of the angle between them, okay? Okay, hold on. Okay, and so the first thing here, this is just fairly weird, okay, is to kind of understand what this is, because I can never remember this formula, okay? But, I just got to remember what it is that I'm trying to do here. And I'll draw a picture of it. So we have some vector A and some vector, B over here. Okay, and then you've got cosine here, or we've got an angle here, theta. Okay, and it doesn't obviously have to be theta, it could be phi or whatever it might be. So, all right, and so this will be the first kind of use of this that we might drive at, would be, so you might want to know, okay, so I'm just going to kind of talk about this a little bit. So first of all, I'm going to, let's do, okay, so I'm going to rearrange this a little bit. So A dot B, okay, equals, I'm going to pull the B out front like this, and then I'm going to have the rest of it here, A times cosine of theta. Okay, and then what I want to do, I can't steal that whole thing. I can't just steal one part of it, is I want to bring this over here, this B, like that. Okay, so all I did was I rearranged the B and the A, and then I brought this B over to the other side of the equation, and I think you'll see that, okay, so what is this now? Okay, so this right here, I can see in my picture above. So, if I've got A cosine theta is this right here. So this is A cosine theta, right? I hope you can see that. Okay, so in other words, this right here, this expression right here, so this thing, either side of that equation is the projection of A onto B. Okay, so if you want to solve for this, okay, if you're like, I want to drive at kind of what is this projection, what is this angle, there's just like 1,000 different ways you can drive at it. If you know this dot product, if you can solve for this, okay, and you know this angle, well, it's just kind of an instant equation, so it depends on what you're looking for. But whenever you're looking for projections or you're given projections, okay, then this is how you can. This is one way you can use it, and we'll work an example in a second. Okay, so that's one of the two uses is for projections. Okay, so one use is for projections. Okay, and then the other use of the dot product, and this is the one that we'll probably see more in this class, is for that angle. Okay, so we would use this to find the angle between two vectors. Okay, so you might have a problem where it's like, oh, here's some pole sticking up out of the ground, and we've got these two cables or even three cables coming down in 3D, and you might want to know, for whatever reason, you might want to know the angle between A and B. Okay, so how do you figure out that angle? Well, you say, oh, okay, well, A dot B, okay, equals A B cosine theta. So then you can rearrange this, and you could say, oh, well, then that means that theta equals A dot B over the magnitude of A times the magnitude of B. Okay, so that's pretty inverse cosine like that. Okay, so that is one way to do it. Now the problem still, from everything that I've done so far, is if you look at both of these equations that I've done, it's like, well, but how do we get at A dot B unless I'm using the other half of the equation? So it's not really very helpful. So here's how you would typically solve this for A dot B of any particular vector, is you would say, okay, well, I've got A dot B, and the way that you solve this, so this is kind of how you calculate it, okay? And this is going to assume that A is a, A in the x direction times the I vector, plus A in the y direction times the j vector, plus A in the z direction times the k unit vector. Okay, and similarly for B, we'll say bx in the I direction plus by in the j direction plus bz in the k direction. Okay, so luckily, the algebra here, once you've got this thing split into its components, is pretty easy. Okay, or at least it's what you would hope it would be, I guess. It's ax bx plus ay by plus az bz. Cool, right? Okay, now notice this is a scalar. Okay, this is a scalar. Okay, all these things add together. Okay, and it loses all direction. Okay, so that's pretty huge. All right, so let's see if I can find a good example, and maybe we can calculate a few of these. All right, so if I just kind of got a random, I just kind of came up with this off the top of my head, and this is a 2D example, we can do it in 3D as well. But if I've got an A and a B, and A is 4i plus 3j, and B is 2i minus 2j. Okay, so 4i are kind of like this, 3j, like that. Okay, 2i and negative 2j. Okay, so when you're looking at this, you should be thinking to yourself, or at least I know I'm thinking to myself, well, if the question is, what is the angle between them? Theta AB equals what? Okay, so here's theta. Okay, now we know already that the angle theta is going to be more or less 90 degrees. Right? It's pretty close, right? If this were 3i plus 3j, we know that we would end up with 90 degrees. But let's go ahead and solve this. So what we do is we would go back to our definition here, and I would say, okay, well, A dot B equals the magnitude of A times the magnitude of B times the cosine of the angle between them. Okay? So I think maybe to simplify this, let's go ahead and get the magnitudes of A and B. Okay, so the magnitude of A, let's see, magnitude of A. Okay, so that's going to be the diagonal basically. So that's going to be 4 squared plus 3 squared square root. Okay, and the magnitude of B will be 2 squared plus negative 2 squared. Negative's not really necessary there. Equals, let's see, I don't even think we need calculators for this. The square root of 8, so that's 2 root 2. And this one is a 3, 4, 5 triangle, so that one's 5. Okay, so good. All right, so that's one part of our little cross product that we need to do. The other part that I want to figure out before I kind of dive into this guy right here is let's go ahead and figure out what A dot B is. A dot B equals. Okay, so I'm going to follow the formula that I did from above. So it's going to be the x terms, so ax. So I'll write it out for you this first time. Ax bx plus ay by. Okay, and so A dot B equals 4 times 2 plus ay, which is going to be, where's ay? Oh, 3, right? Times by, which is negative 2. Okay, so A dot B equals 8 minus 6, which is 2. Okay? And notice it's a scalar. All right, so that means we're cooking with gas. So we can drive this thing down here, and I'm ready to plug some numbers in. Okay, so I'm going to say, well, A dot B is 2 equals the magnitude of A, which is 5. It's the magnitude of B, which is 2 root 2. And then cosine theta. Okay, so theta then equals the inverse cosine. Okay, just doing the little algebra here of 5 over the square root of 2. I believe that's right. Yeah, so theta equals. And it appears we have an error. Okay, one good way to know that you have an error is if you plug it in the calculator, it tells you have an error. You've probably done something wrong. And I have. So I got a little quick and loose with the algebra. Okay, hopefully you caught that. And this should actually be 2 over 5 root 2. Okay? No, got 2 loose again. Right? Let's see. So 1 over 5 root 2. And we end up with theta equals 73.570, which is 73.1 degrees. Okay? Now here's a question. Would I have gotten the same thing if I had done B cross A? Or, excuse me, B dot A. So if I had been looking for theta, and so this was theta from A to B, I guess, the way I've written it. Okay, so let's suppose theta is going that way. Would I have gotten the same thing if I had gone theta this way? Okay, or would I have gotten a negative sign? Well, let's think about it. I don't even think we need to do the whole thing. But let's suppose I did B dot A equals magnitude of B, this is magnitude of A, times the cosine of that angle. Okay? Well, let's look at this, and let's imagine that the B's and the A's were in different position. Would we get a different answer? Okay, that means that these would do like that, and these would do like that. This would be the same. Okay, hopefully you can see that. Oh, sorry, that means this side would be the same. The magnitude of B is the same no matter what. The magnitude of A is the same. So the angle would be the same no matter what. We would just end up with the exact same number, okay? So B dot A or A dot B, okay, same. Okay, and you can use it either way, okay? Okay, so that's how we do it. Let's do one in 3D, and then we'll just, we'll move on with our lives, I think. So unless I can think of a good reason we might want to use this for projections. Okay, so let us suppose, I'm just going to draw this problem here. All right, so we've got some sort of pole, and it's stuck in the ground. And in order to keep it up, we're going to support it by some guy lines, right? So the guy lines are going to go from some point on the ground. So let's suppose this sucker is like 10 meters tall, or just 10 units. We won't deal with, what do you call it right now? Units. So we'll say this thing is 2 up and 2 over from the origin. And let's suppose we've got another one going off in this direction, okay? And it's somewhere on the y-axis, okay? And let's just say that's 7 over. And then we've got a last one that's going off, and it's, I don't know, somewhere, maybe it's like right there, so it's, and it's, I don't know, coming in right there, and it's coming in right there. So it's 1 over here, and it's 5 over there. Okay, and so for whatever reason, you're working this problem, and you need an angle, right? You're just sitting there, and for some reason you're stuck, and you're like, I need the angle between these two guy lines. Okay, sometimes the problem might be the point of the problem, is just to ask you the angle, but sometimes it won't. So let's just go ahead, and I'm going to name these two guidelines because that's going to help me to solve the problem, okay? And what we're going to do is we are just going to use the formulation for the dot product. But before we do that, we need to define our vectors, okay? So A is defined going basically in that direction, okay? So it's kind of got an arrowhead going down. It's pointing down, and B is pointing down the other way. So let's go ahead and define A. So A in the x direction from the top where it begins to where it goes into the ground. In the x direction, it goes over 2 in the I, 2 i's. Okay, how far does it go in the y direction? Well, it goes 2 in the y, so 2j. What about in the k direction? Well, it goes down 10, right? So minus 10k. Okay, now if we've got b, okay, similarly, b in the x direction is, let's see, this is the x direction right here. Okay, so it's going to be negative 5. Okay, in the y direction, it's going positive 1, 1j. And in the k direction, it's coming down that same 10, so minus 10k. Okay, any guesses on the angle on this sucker? From the drawing, it's kind of hard to tell. But it's basically coming down 10, and as it comes down 10, the spread is becoming almost 7 in the x direction, right? If we go from this line to this line, okay, that's 7. So, it's a little bit of spread in the y direction, not much. It's just like a spread of 1 in the y direction. So we might be approaching 45, but probably not. We're going to be less than 45. Anyway, so here's your definition. So it's going to be A with a little arrow, if I knew how to draw arrows, but of course I just know how to draw scribbly scratch. Okay, A dot B equals the magnitude of A. It's the magnitude of B. The cosine of the angle. Okay, and remember, it doesn't matter which one's A, which one's B. We just got to stay consistent through this. So A dot B. So that's going to be the x values of A and B. So AX, BX. So it's going to be 2 times negative 5 times plus BX, or AY, BY. So AY is 2, BY is 1. And then, what's the last one? AZ, BZ. So that's going to be negative 10, negative 10. Okay, equals. Okay, now we want to do the magnitude of A. So we use the Pythagorean theorem for that. So the magnitude of A is, let's see. So that's going to be 2 squared plus 2 squared minus, plus 10 squared. Noting that we don't need to worry about that negative sign because we're squaring it. Okay, and we're going to multiply that times the square root of negative 5. Again, the negative doesn't matter. Plus 1 squared plus negative 10 squared. Noting, again, we don't need that negative. Okay, cosine of theta. Okay, so that's a lot of noise. All right, so I'll just kind of pause it and the algebra will pop through. All right, so just, following the algebra along, we calculate the dot product, which is whatever that total is. Like I said, total is 92. And then using some nice little algebra, kind of keeping things under that square root to just kind of save myself a little bit of energy. So this is 108, this is 126. So we get cosine of theta equals this ratio. And we what do you call it? We take that square root and inverse cosine both sides. So we get 37.9 degrees. So, I guessed that it was going to be a little bit less than 45, and I guess that qualifies. I don't know. All right, so anyway, so I'm going to go to your homework now, and I'm just going to work from the review problems that I posted onto Connect, if you guys just have something to study for the exam. And I'm just going to work random problems. So I'm going to kind of roll some dice and just see what comes up. Okay, so I'll do one from chapter 2, one from chapter 3, one from chapter 2, one from chapter 3, until we run out of time. Okay, so I'll just pause. Well, let's go find a nice spot. Okay, so here we go. This is the spot, and we will see the problem appear. Okay, so this is chapter 2 review, question 7 through 12. And so what we've got some sort of, these little frames they love for these class. Anyway, hopefully you can imagine it. So there's kind of a pin right here, and there's a, what we'll ultimately discover is kind of it doesn't matter. Anyway, so we've got some sort of bar or something here, and it can rotate around this pin if it wanted to. So if you want to, you could push it this way or that way, and it would move, assuming there was nothing else pushing on it. But because those things don't exist, aren't there, you can't do that, right? So let's just get rid of that. Okay, and then we've got a rope, and the rope is, or cable, and the cable is attached to the end of this thing, and it's going all the way over here to this point B. And then we've got a force coming off of it going this way, which is force P. And what they give us is they say P equals 335 pounds alpha, so that's this angle right here, that's 55 degrees, and everything's at equilibrium. So what they want to know is they want you to solve, draw a free body diagram to solve for TBC, and then they want you to solve for TBC and FAC. Now, the way they use it in the book is they say, what is the magnitude of the force for this part? It's a little bit confusing. I'll be much more clear about which force I want when I create the test. Anyway, so we're going to go ahead and solve this. And I might solve this a couple different ways just to kind of give you the idea of what can be done here. But we're going to start with a free body diagram, and we're going to do a free body diagram that can basically solve for anything. Okay, so I'm going to do this first the way that I would do it, and then I'm going to kind of do it the way that the book does it. So if we want TBC, that tells us that the tension in this cable from B to C, that means essentially I'm going to have to cut this cable like right here. Somewhere along the cable I'm going to have to cut it, because that's the only way that that force is going to be external to the system. If I cut it and I keep this side of the diagram, I'm not really going to have much to go with, right? So let's just imagine I just draw that cable. Or maybe I draw the cable and the thing it's attached to, right? And then there's nothing else in the universe outside of that. Okay, well now I've got a tension going this way, T, BC, or CB, I guess, or whatever you want to call it. And then I've got two forces here on this pin or forget even that pin, I've got this wall pushing on this thing in some way. Okay, I can't solve this. Okay, so that's no good. So we're not going to do that. So then the logical thing instead is to cut our system here, here, and basically this is our system, like this. Okay, that's our system, because that we can work with, right? So here's our point C. Okay, and we've got something going off this way, and it has been chopped. And we've got something going this way, and it has been chopped. And then we've got a force going off this way. That's P. Okay, and it's off at 20 degrees. Okay, this is at 55 degrees. Okay, and that's TBC. TBC. And then we've got a force here, and I don't know which way it's going to go, but I'm going to go ahead and assume, actually we do know which way it's going to go. It's going to have to go this way. FBC. Okay, now, and this kind of came up on a little bit on one of the homeworks that I graded, and I don't expect you all to have this intuition yet of what I just said, where I said that I could tell which way this force is. But what I want you to do is I want you to start thinking about this if you can, is that imagine this force went the other way. If the force went this way, so it went the other way. Well, the force goes the other way, the resultant of these three forces cannot be zero, right? Because, I'm going to draw and imagine, because, let's see, so any axis that I could draw, it has to come up to zero, right? So let's imagine, I'm going to draw some axes right here and right here. Okay, any axes I can draw. So let's suppose I grab these and I bring them over here and I put them like this. Okay, can you see that no matter what I do, if one of these directions is determined as being like x, can you see that there's no way for x to be balanced if the force down here is going in this direction? Because all the forces are in the negative x direction. Okay, now they could balance in this version of y, but they cannot balance in this version of x. Okay, so that means that the force cannot go in that direction. So if I erase that bit, that red tail that I drew, okay, and it goes the other way, well, now you can see in the x direction, well, I've got a positive x and I got negative x. Tau BC and P are both in the negative x, and FBC is in the positive x. And in the y direction, I've got both positive y's and negative y's. So this can balance. Okay, so I'm going to go ahead and get rid of this because we don't really need that. So I'm just going to erase it. It'll probably take me a minute or two for this eraser to learn how to erase, because that's what these things do. Anyway, so that's just kind of some of the intuition. Okay, so that cannot be at equilibrium if you don't either have no forces in a direction or opposing forces. All right, so there's your free body diagram. Boom, we drew all the forces. Technically there should be a weight, but unless they tell you something about the weight, you're just going to kind of have to assume that there is no weight. Okay, so the other way that you can solve these things, so that's the solution for A. But another way that you can solve these problems is you can do, the force triangle. So we can go FBC. Oh no, I want I want some white. Okay, so let's get some white. So two ways to solve these, and the other one is like this. FBC goes that way. What's its angle, by the way? Let's get its angle over here. 30 degrees, okay. So it's 30 degrees here. Okay, and then we can go, TBC is going this way. TBC. And then actually it's gonna have to go a little bit longer than that. And then P is gonna come back this way. Okay, and P has an angle here of 20 degrees. Okay, and tau BC is right here, and that's 55 degrees. Okay, so these are the two ways that we can solve these. Okay, we can either do a forced triangle, or whatever those are called, or we can do just a free body diagram. Okay, the forced triangle is kind of going to be quicker, I think, but the free body diagram is much more universal. So I would always solve this with a free body diagram. It's kind of up to you. You can solve, you can do whatever you want, but we're going to do both. Okay, so I'll go ahead and do the forced triangle real quick because I think that's pretty straightforward. Oh, this line right here is P, which I think was 550, 335, excuse me. This is 335 pounds. So I'm going to do this forced triangle first just because it's the quicker of the two in this case. All right, so I'm going to note that this angle right here and this angle are opposite angles. So this is going to be 20 degrees, which means this whole angle is 50 degrees, right? So that's cool. And then we'll also note that this 30-degree angle and this right here are opposite angles, or whatever they call them, which means that this one, because the 55 and the 30 and this one have to add up to 180, that means this one's 95 degrees. Okay. And then, so now we've got 50 and 95, so the three interior angles of a triangle need to add up to 180. So 50 plus 95 is 145. So that gives me, this one has to be, what, 35? 35 degrees. Okay, so now we have all the interior angles, and we know one side, which means we can use the law of sines. So we'll go with, so P over the sine of 95 equals TBC over its opposite angle, sine of 50, equals FBC. Wait, TBC, FBC. Okay, somewhere we've got a name wrong here. Let's see if we can't figure that out. FBC, it shouldn't be FAC. Okay, so this should be an A, C over here, and this should be an AC over here. Okay, so this should be AC. Okay, over the angle across from it. So the angle across from it is 35, sine 35. Okay, so this will allow us to basically solve for whatever we want. So if in place of P, I write the, if you don't want to allow me to erase, I'll just do it this way. I write 335 pounds. Okay, then I can basically do this equation, and then I can do this equation, and that will solve this whole problem. So I'll do 335 pounds over sine 95 equals, I'll just pause it and have this pop up. Okay, so doing the algebra, basically I set this first term equal to the second term, and I solve this equation. And then I set the first term equal to the third term, and I solve this equation. Well, I gotta kind of zoom around a little bit, and I solve this equation. Okay, and so we get the two values. Okay, and that's really fairly quick and easy if you do the forced triangle. More commonly, though, you're going to want to be able to do this with a free body diagram, so I'm going to go ahead and solve it that way. Okay, and so what we're going to do in this case is I'm going to break each of these up. So TBC, okay, equals, I'm just going to break them up using the trig, okay, equals, let's see, so the x component of that is going to be TBC, okay, the magnitude of that, times, let's see, so that would be the sine of 55 degrees, okay, in the negative I direction. Okay, and then plus TBC, and the plus is because it's in the positive y direction, and cosine, because that would be the adjacent side to that angle, cosine of 55 to the j. Okay, now I'm going to do FAC equals, okay, so in the x direction is it's positive, so positive FAC. Okay, and that the side of that triangle, so if we do it like that, the x direction is the opposite, so it's going to be a sine of 30 I plus FAC times, now this side is the adjacent side, so that'll be cosine of 30 times j, and then we'll have P, okay, equals, and I'm going to go ahead and put, well, I'll just use P for now. And let's put in the 335, equals 335 pounds. Okay, it's in the positive x direction. And this is the opposite, so it's going to be sine of 20 I. And in the j direction, this is negative, so minus 335 pounds. And that's going to be cosine 20 in the j. Okay, so what I can say is the sum of the forces equals 0, which means TBC plus FAC plus P equals 0, and I can go in directions. So sum of the forces in the x equals 0, sum of the forces in the y equals 0, if I assume that this is x and this is y. Okay, so that means that, and I'm going to use a calculator here so I don't have to write down the sine of 55 and cosine of 30 and blah blah blah. I'm just going to go ahead and start plugging some numbers in here. So in the x direction, I got this one, so that's going to be negative 0.81915 tension BC, or the magnitude of tension BC. Okay, and then I'm going to add this one. Okay, so that's 0.5. The sine of 30 is a half. Okay, which you were probably supposed to memorize in high school, but a lot of us forget that. Yeah, I stare at it too, so I'm not going to play all high and mighty about that. And then I'll add this last P force right here. Okay, but I'm going to plug it into the calculator so that I actually know what that value is. Okay, and we get our x direction equation. Okay, now this is kind of an ugly equation. So what we're going to do is we're going to have an equation in x, and we'll have a similarly ugly equation in y, and I'm going to want to solve one of these and plug it into the other one. So I'm going to go ahead and solve this one for FAC, and then and that way we'll have something that we can plug into the y direction. So I'm just going to pause it while I do the algebra. All right, so rearranging and solving for FAC, I get FAC equals 1.6383 TBC minus 229.16 pounds. So this is auspicious because 229 is my lucky number. So that's a really good sign. Okay, so what I'm going to do now is I'm going to move this one over a little bit because we're going to need a little bit of space here. I'm going to try to leave it such that we can barely see what we're adding up, which are these things right over here. Okay. So basically, we're gonna start with this first one. I'm gonna say, well, TBC, okay, cosine 55. I think earlier I didn't do cosines, right? I just put in the numbers. So let's just go ahead and put those numbers in. Okay, and then we're gonna have a plus sign, and we'll have cosine of 30, which is like 0.866, I think. Cosine of 30 is 0.86603, 0.86603 times the magnitude of AC. Okay, and then, so that's this one, and then we've got one more, and that's a minus sign, minus 335 cosine 20, which is 314.80. 314.80 pounds equals 0. Okay, so now that we've got this equation, it is no more or less ugly than it was in the y direction. So notice here's the x and here's the y. They're the exact same ugliness. However, since I have this one all ready to go, I'm just going to plug it in right there, and I'm going to solve for TBC. So let's just kind of zoom in and let's just do this. Okay, so I know it's not fun doing all this necessarily. Well, you know, I don't know. It's a little zen. Okay, you know, if you want to zoom through this, you know, this part, I don't blame you. Okay. Okay, minus 229.16 pounds. Okay. Okay, and then let's see, minus this equals 0. 314.80 pounds equals 0. So at this point, we only have one unknown in this equation, so we can solve it. Okay, so again, I'm just going to pause it. The algebra will pop out. All right, so just kind of plugging and chugging through that problem, and we get the tau BC, or TBC, excuse me, equals 258 pounds, which I'm almost certain is the answer we got above. If not, we made a mistake. So TBC, 258 pounds. Okay, so that's good. And if we want FAC, then what we'll do is we'll go back up to this original equation right here. And we'll say, well, FAC equals 1.6383 times TBC, which is 257.61 pounds. Okay, minus my lucky number, 229.16 pounds. Okay, and that will solve out nicely for us. Okay, 193 pounds. Okay, and I think if we go up here, you'll see this is exactly the number we got. In fact, 192.88. So by keeping 5 sig figs, we maintained the exact same answer. Okay, so it works. Okay, obviously, I think, especially if you zoom way out, you can see. Look at this method. Ouch. Right, compared to this method. Okay, but this is going to be the one that we're going to end up doing this one more often. And the reason for that is because, you know, if you have more than three forces, you can't do a triangle. The other reason is if you're in 3D, this triangle becomes very hard to figure out. One thing I want to note is, based on what I was saying earlier in this video, notice that in the X and the Y, there's at least one negative and one positive in every direction. So, you know, in the X direction, we've got negative, positive, positive, so they can balance. In the Y direction, we've got positive, negative, positive, negative, okay? If there wasn't at least one in each direction, like, we're not going to be able to balance, okay? So sometimes this will work out because you'll discover that, oh, this force actually is just a sign error, okay? And so you'll end up solving for that, and you'll get a negative sign, and it'll tell you that you assumed the wrong direction, okay? So anyway, that's chapter 2, questions 7 through 12. And then I'm going to go to chapter 3, and we'll just do a random one from that chapter. Okay, so I'm going to highly recommend that you all pull out your book for this to kind of get a better image of this, you know, kind of this drawing, because I can only draw it so well. You know, this is a random number generator. So random number told me to do was 19. There's 19 questions. So 18 and 19 were together, so we're going to do both of those. So this is from chapter 3, numbers 18 and 19. And so what we've got is we've got a pencil here, kind of at point B. I'll draw it in yellow. And there's a force B. I guess it's not really a point B, but there's a force B, which is currently undefined. And that force is shoving this pencil in, okay, into this pencil sharpener. You guys probably haven't really used too many pencil sharpeners. And there's a 1 foot-pound moment around that pencil. And in the meantime, okay, I'm assuming that's an applied moment. And in the meantime, you know, here's your pencil sharpener handle, okay? And it's got 3 forces on it. Or really, it's got 1 force, the C force. But the C force is happening, you know, at point C, and it's got a component in the X direction, the positive X direction, the negative Y direction, and the negative Z direction, okay? And so this is a pretty challenging problem, and we've got some lines all over it showing us how far things are apart. You know, so from point A, over here to point C is 3.5 inches along the x-axis. And then, yes, and then from point, let's see, from point A to point C along the y-axis, the z-axis, excuse me, is 1.75 inches. Although really I drew that arrow just a midge too long. So let's kind of shorten that if we can. And then from point C to wherever they're applying point B, that's 2 inches. So notice that the, this is not drawn to scale. Okay, this is my drawing. It's a little quick and dirty. But I highly recommend that you go look at the drawing in your book, because that should help with this. So what we want to know, okay, in part A is, okay, so what we want to show, at least in this first part, and we'll get to the second part later. So this is our givens. Okay, so in the second part, we want to show that the sum of the moments and the sum of the forces at B and C. Okay, so we've got basically, a force at C that's kind of split into 3 parts. And we've got and plus this force at B, and the 1 pound moment is equivalent to a resultant force of 2.6 in the I plus, something in the J, and negative 0.7 pounds K, so negative Z direction. And then in the resultant moment or couple around point A would be something in the X direction, 1 foot-pound in the J direction, and negative 0.72 pounds force foot in K. Okay, so let's zoom out so we can look at our picture, and let's kind of formulate a strategy here. If you just let me zoom out, you punk. All right, so we can formulate a strategy on how we're going to do this. Okay, so I think the strategy here is we're going to try to match up what we know with kind of what we're given. So we're given this complicated thing. So I'm going to start with the resultant force because it's a lot easier. By the way, I happen to land on a very difficult problem, and there's some real beauty in that. So let's just roll with it. Okay, so the resultant force, okay, that's the sum of the forces, right? So what forces do we have on this? Well, we've got B. Let's see, what other forces do we have? And we've got C. Okay, we've only got 2 forces. Now C's got 3 components to it, and we know the direction of the components. But it's pretty straightforward. So this is going to be Bx I plus Cx I plus Cy times J plus Cz times K. Okay, so, well, I guess we don't need those lines over the top since we have. Okay, so yeah, so we're looking pretty good here. And what's cool here is that if I split this thing apart, I can say the resultant is, well, these two are the x directions. So that's going to be Bx plus Cx, okay, times I, plus Cy in the J, plus Cz in the K. And so if we compare that to what we know from up here, right, I can say that these two add up to 2.6 pounds. Okay, Cy, well, that's just Ry. And Cz, okay, is negative 0.7 pounds. Okay, so that's pretty helpful, right? Okay. And I'm kind of making a sloppy sign thing here, so I think I'm gonna revert to doing a more rigorous sign thing. Come on, let me grab this. Okay, so I'm gonna assume that these are drawn as correctly, and so as such, the Cy and the Cz are both negative. So let's go ahead and put those in as negative. So let's delete these things here. Let's make them negative. Okay, so we'll be a little bit more rigorous here. All right, so then it kind of becomes, fair to say that we now know a good bit. We can say that Bx plus Cx equals 2.6. So I'll just go ahead and write out what we know. So Bx plus Cx equals 2.6 pounds. Okay, negative Cy negative cy equals ry, and cz equals positive 0.7, because negative cz equals negative 0.7, okay? So those are our three equations, okay, or three things that we know, okay? Noting that this sign right here means only that we've assumed the correct direction, okay? And it told us that the direction was downwards, okay? So we just got to deal with that. All right, so now we got to do the harder part, which is the moments. And we're going to do kind of the same idea here, but, you know, moments are trickier. I mean, there's just no way around it. So we're going to start in the x direction, and I'm going to call this moments, I guess the sum of the moments in the x direction at point A, okay, because that's really what this was all about, okay? I guess, you know, the resultant at A, I should have put an A in there, okay? So the moments at point A. Okay, so in x direction. So what we're looking at right now is we're trying to imagine this line right here, this line that I'm drawing, and what is going to make things spin about that line. And the way we think about our direction is if we were looking directly down that line, okay, if it's clockwise going down that thing, during that thing, so if it's going like, it's causing things to go that way around it, that's like kind of over the top, then, so that would be clockwise if we're sitting over here looking, then that's going to be negative. And if it's causing things to go this way, again over the top, okay, that would be counterclockwise, and that would be positive. Okay, so which of these forces are having any effect on causing things to spin in that direction? So if you look at B, for example, B relative to A is, you know, it's in the XY plane, so it's not really going to cause it to spin around this x-axis. B is going to cause it to spin, well, okay, let's just draw it on the whole thing. But, you know, B, I'll do it in yellow and I'll make it really big. Okay, B is going to make it do like that, right, relative to A. Okay, and it's going to stay in that XZ plane, so it's not really going to cause any spinning around the x-axis. Okay, so anything that remains in the XZ plane is not going to cause any spinning around the x-axis. So note that CX is going to do the same thing that B is doing, so I could draw that the same way. Okay, CZ is going to do the same thing as well, so they're all kind of making that happen. Okay, CY in the J. Okay, now note that thing, okay, is maybe causing it to rotate in one of these two directions. Okay, and it looks to me like it's going to kind of follow this thing. So if I were to imagine that thing's going out of the XZ plane and it's causing things to rotate, and it's causing things to rotate counterclockwise. It's going to make things rotate this way, okay, around that axis. Okay, so that means because it's counterclockwise, it gets a positive sign. So we're going to get a positive. And what I want to think about is that's going to be CY, okay? And then how far away is that CY from, you know, it's on a right angle, so how far away is it? What's the moment arm? How far is it from here to here? 1.75 inches. So 1.75 divided by 12, so that's the number of feet. Okay? And do we have anything else working in that direction? Well, we've also got this torque, this 1 pound-foot that's being applied right there. So that is that also the same direction? That is also the same direction. So that would be plus 1 foot-pound, foot-pound. Okay, and that's our moments in the x direction. Okay, noting from what we have above, okay, that is just going to be equal to something called mx, okay, because that was what was given. Okay, so this is an equation right here. Okay, now we'll do MYA. I think MYA, if I remember correctly, is the more difficult one. And it is, because look at all those big yellow lines that I drew. All of those are in the XZ plane, so they're all going around the y-axis. Now notice this one, and this one. Well, they're all going, let's see, what direction is that? So if I imagine I have an eye, and I'm looking straight down this y, those are all going, if I was looking straight down, those are all going counterclockwise. They're all positive. All three of those are positive. Okay, so let's start with B. Its moment arm is from here to there, so it's a right angle distance. Okay, since all these things are happening at right angles. So that is a total of 3.75 inches. So that's going to be B times 3.75 over 12. That's the number of feet. Okay, so that one has a positive sign. And then we got to get these C's. So let's see, we've got CZ times K, and that's going this way. So its moment arm is from here. It's a perpendicular distance, right? So that's 3.5 inches. So that's CZ plus CZ times, what do we say, 3.5 over 12. 3.5 over 12 feet. Okay, and the last one is this CX. So notice CX is also perpendicular. Okay, so its moment arm is from CX, okay, or from the line of action of the force to the thing we're taking the moment around, okay, and that is 1.75 inches. So plus CX times 1.75 over 12 feet. Whew. Okay, that's brutal. Okay, and so that's in the the Y direction, and we'll notice that all of that adds up to 1 pound-foot. Okay, equals 1 foot-pound. Okay, foot-pound. Okay, so this is another equation. Okay, you can see we're getting lots of equations here. And then the last one is we have to do mz times a. Okay, and so we're going to zoom in there. Let's see, where's z, the z direction. So we're asking ourselves, what's going to cause things to rotate around this line right here? That's the z-axis. And again, we want to imagine we're looking down that axis. And as we look down that axis, what direction is it going to cause it to rotate? And so let's see, the only thing that is going to do that is this force right here, because it's going downwards. And I think we can imagine that if we had that force, it would make things go that way around it. Okay? And so that way would be, if this is where we were sitting, that would be what? Clockwise, right? Clockwise, clockwise, clockwise. Yes, so that would be a negative sign. Okay, so negative, and that's going to be Cy, okay, times its moment arm, which is going to be from that Z to the line of action of the force, which looks like it's 3.5 over 12, okay? And now again, we remember what we know, which is we know from up here that that equals negative 0.72 foot-pounds. Okay, so that's another equation. Woo-hoo. Okay, so we've got a lot of equations here. So we want to start solving this, and the way we're going to do this is we're just going to be strategic. We're just going to go with the ones that we know are easiest. Okay, so like right now, I already know that CZ is positive 0.7. Okay, so that's good. Are there any of those other equations? Equation one unknown? This one is, the last one we just did is, so I can solve for Cy right here if I wanted to, and I can say, well, Cy from the line above it, just doing a little algebra. So Cy is 2.47 pounds. Okay, so now we know two of our C's. So what else can we do with that? Well, I could plug Cy, for example, in right here, but I'm not sure that would help me very much because I don't know what mx is. Okay, so let's see, I could plug, I know Cy and Cz. Yachi machi. Okay, so yeah, so this took a little bit of staring. So one of the things I need to do is I forgot I have an x right there. So what I want to do is I want to take this equation right here, and I want to plug into it this equation. Okay, and I want to plug into it Cz right here. Okay, so basically I want to take this equation and plug it into this equation. Okay, so I'm going to zoom out a little bit just to give myself a little bit of space down, or maybe not zoom out, but move a little bit. Okay, and I'll show you how that's done. okay? So we're going to start by bx is going to be, based on this, bx is going to be 2.6 minus cx. So 2.6 minus cx, okay, and I'm putting that right here, times 3.75 over 12, plus cz, which is 0.7, sorry, that should have a little pound symbol on it, pounds, times 3.5 over 12, okay, plus cx times 1.75 over 12 feet equals 1 foot-pound. Okay, and this way I can solve for cx. So again, I'm just going to pause it and do the algebra. All right, so a little plug and chug. Okay, plugging things in, moving things around, etc., multiplying, solving for cx. Once we have cx, I'm going to go ahead and I'm going to use this relation up here. I'm going to notice that bx plus cx equals 2.6. So 2.6 minus 0.975. Well, don't even need a calculator for that. But bx, okay, or b, there's only really one direction for b. So bx is 1.625 pounds. Okay, so now if we know that, I think we know everything except for cy. Oh no, we know cy, so we got cy, cz, cx, and bx. Okay, so I will note that my answer disagrees with the answer that the book gives, and I can't really explain it. I've stared at it. I'm going to assume that I'm correct, because I don't see an error. Doesn't mean there isn't one. There may be a sign error in here or something, or an algebra. That's how it goes. Note that no one expects you to be perfect. No one expects me to. Well, maybe you guys expect me to be perfect. I'm clearly not perfect. But there's an error in here somewhere, maybe. Okay, but the procedure is exactly correct. Okay, so the procedure is correct. And if it is an algebra error on an exam, I would keep looking until I find it. Or if I can't find it, I'll just write algebra minus 1, and you'll lose 1 point out of 10, right? So don't sweat it too much, okay? And on an exam, of course, I will definitely find the error. Anyway, so if this were the final answer, then the way you would present it is you would say, well, B equals 1.625 pounds in the I direction, and C equals, let's see here, 0.975 I. The Y is 2.47 J, and the K is, where's the K direction? Oh, 0.7, 0.7. Now you'll notice I didn't put signs on any of these, and because all of these, when they solved, they give us positive signs, all that told us is that we assumed the correct direction when we drew the problem. So if we go up to the original drawing, you'll notice that CY was acting downwards right here, CZ is acting downwards, and CX is acting positive. So ultimately we're going to write positive, negative, negative. Okay. You'll note that when we really get into it, for me, the book did this, made that drawing. You will never see me make that drawing. When I make the drawings, I always assume my forces are positive. That way, if they give me a negative sign, it tells me that the way I assumed it was incorrect, and that'll make it negative. Okay. And I still remember the lady who taught me statics teaching me to do it that way. So that was the way that that I would have done it. Okay. So the second part of this for the textbook then is much easier. Is it says, well, so this would be the second part of this problem would be ry equals what, and mx equals what. Okay, and so that's as simple as plugging your values in right here. So in assuming I'm correct, which I'm not sure that I am, we'll use this equation right here that negative cy equals ry. So cy, where are you, cy? Is negative 2.47, so ry is 2. Wait, ry was, cy was, so it's going to be negative, okay? And then mx, okay, we're going to go look at, where's that equation from mx? Oh, it's this one right here. So for cy, I'm going to plug in whatever we got with 2.47. So I'm going to plug that in right here. Okay, and solve for mx. Okay, and if we do that, we end up with mx equals 1.36 foot-pounds. Okay. Noting that, you know, this answer is, if the first half was wrong, this half is based on the first half. So, you know, it's going to disagree with the book. If I stare at the book, yeah, well, you know, it's got me off by a factor of 1,000. That's really interesting. That's really weird. Okay. Anyway, if the error started, if you did this and like let's say you had an algebra problem over here, and you're like, oh my God, it screwed up the whole problem. And when you get over here when I'm grading it, you'll see me, I'll write on the test DDC, which means don't double count, which means these answers are not right, but I'm not taking points off because I already took points off over here. Okay. So anyway, so we'll do another one from chapter 4 now to kind of get, to kind of close this whole thing out. You know, the computer's getting slow because it's getting tired. So let's see what we can find. Anyway, so we're actually not doing chapter 4, so I was getting ahead of myself. So I give you a problem out of chapter 2, a problem out of chapter 3. The one out of chapter 3 was really a doozy. Hopefully it gave you kind of an idea of how these things work. If you want more of these, just ask me. You know, I can give you more examples if you like, or if you prefer, I can just work some out on a sheet of paper and you can try to follow along. But yeah, I think we're going to go ahead and call it here. This thing's freezing, and you know, it's freezing constantly. So maybe I'll make you another one before the test. So anyway, good luck with studying, and you know, if you need me any other time, please let me know. I don't mind. It's not a big deal. You know, I am here to help you. So take advantage of that. And it won't even hurt my feelings if you're like, I don't like your lectures and I want to go talk to somebody else. Well, let me know. Maybe I can help you find somebody who can help you with this. But yeah, so whatever you need. Okay. I don't take it personally. I mean, as long as you don't cuss me out, you know, just, you know, say, hey, you know, I want help with this, and I don't think you're the person for the job. And you know, that'll make me a little sad, but you know, let's get over it. The goal is to get you through this course with the grade you want, and more importantly, with the knowledge that you need to move forward. So again, take care of yourself, and I'll see y'all next time. All right.